Hello guys, welcome to our channel of Sciences and Mathematics. I'm excited today that we're meeting again to discuss a new topic. Of course, today we're going to discuss on a fundamental topic. This is going to lay a basis for us in discussing the topic of organic chemistry. Of course, this topic will be very much essential. We'll be entailing capturing the main concepts that we have had under the study of an atom and a bit of history so that it's going to assist us when we mention about one aspect or another, we'll be able to be understanding where that one came from. So in today's discussion, it will mainly be a basis upon which we will build on the other topics which are going to come that entail organic chemistry. So for that case, welcome and feel free to question in the comment section. Of course, I had said that I'm going to put a link of related content that we have posted about this particular topic. So in that case, this is going to lead us into the topic of organic chemistry. But as I said, it's going to entail a discussion of different aspects, which of course will assist us not repeating some of the concepts, or else when we shall be coming across such a kind of concepts, it will be easier for us to discuss instead of going back again to just have a recap. So in that case, as we know, or as we discussed before, this subject of chemistry as a subject entails the study of matter, its composition, properties of matter, the structure of matter, the changes that matter undergoes, and finally the laws that are governing these particular changes and all aspects that entails these particular concepts. So when you look at chemistry as a subject, as we have said, that if indeed it entails these particular aspects of finding the composition, properties, structure, changes that matter undergoes, and the laws that are governing these particular changes, then in actual sense we are talking about studying about this branch of chemistry and all these particular aspects that entails or pertains to that particular subject. So this one gives us a reason as to why we should of course have a look at some of the properties of matter, what are some of the laws that are governing compositions, and what are some of the parameters that we should use in order to describe the properties of matter. How is matter represented in form of structure? What are some of the changes it undergoes? And what are some of the governing laws that you have to apply or which are applicable as much as organic chemistry is concerned? So in that case, as we just said, matter is made up of very tiny units or fundamental units that we call atoms. So in this sense, an atom makes up of a basic building block of matter. So when we talk about the word basic, which means it's a fundamental building block of matter. Now in that sense, we are going to look at the characteristic of atoms as we go ahead. But in this case, we're trying to see how an atom will lead to building of other blocks of matter we talked about structure. So for that case, discussing the basis of an atom is going to give us a clue on how we're going to form other structures that are developing from an atom. So in this case, this atom is the smallest unit of matter that cannot be divided by any chemical means. So in this case, if this is the smallest part of matter that cannot be divided into further units by another chemical means, this one leads us to another part of matter that we call an element. So in an essence, atoms of matter, similar atoms of matter, leads to what we call an element. So in this case, the concept of an element comes from comes from the Dalton's atomic theory. So this was John Dalton who came up with the Dalton's atomic theory. To describe matter, and in particular an atom. So for that case, Dalton's postulate or an argument is that atoms of elements are identical. So which means an element consists of identical atoms, which of course displays similar properties and the composition. So for that case, according to John Dalton's atomic theory, atoms of elements consists or are all identical. So in this sense, when we have atoms and elements, so in actual sense, an element, this basically is a substance that cannot be broken This is a substance that cannot be broken down into simpler substance by ordinary means. So this element is a substance that cannot be broken down into simpler substance by ordinary means. By ordinary means, of course, this is an intentional use of a word. We are going to see some of the conditions under which maybe an element can maybe be broken, or can be able to be, the division of an element can be able to be influenced or maybe altered when we come to some of the topics like radioactivity. So in that case, organic chemistry is going to give us a clue on how these particular elements affect the physical properties or the characteristics of what we refer to as organic compounds. So if we look at matter, in that case, we said that matter refers to anything that has mass and occupies space. So what we refer to as matter has got mass and occupies space. So in this sense, if we say that the study of chemistry entails the study of matter and the interactions between matter and energy, so if the study of chemistry entails the study of matter and energy, it is basic for us to understand that this particular concept of energy that we are talking about can present itself in different forms in as much as, or insofar as chemistry is concerned. So the different forms of energy that we know, we've got light, which is a form of energy. Heat is a form of energy. Sound is a form of energy. We have also what we call chemical and the mechanical energy. Chemical and mechanical energy. And lastly, electrical and nuclear energy. So if energy is an aspect that interacts with matter, so for that case, or maybe if we are able to get energy from chemical reactions, then that one will form a basis for us to study about the concept of energy and matter in organic chemistry. So that one will be very much essential. So in that case, we are going also to look at a different concept. And this concept is also going to be in line with what we have discussed, and also try to narrow down to our topic of discussion for today. So as we talked about an atom, there are several ways in which we are going to be required to represent this particular atom or an element in organic chemistry. So that one requires us to look at it in details and know the characteristics of this particular aspect of matter that we call an element. Of course, this is going to be biased at the atomic level. And as we said, an atom of an element is made up of electrons, neutrons, and protons. Now this all in general we refer to them as subatomic particles. Now, as we said about the brief history of this, of course we are not going to discuss in details, but it will be pertinent for us to see that throughout the history, as the discovery of the electrons were concerned, this was done by J.J. Thomson, who discovered the negatively charged particle in an atom and called them electrons. Of course, this was done by the use of a cathode ray tube experiment. So that led to the discovery of electrons we are going to see. But for that case, it's good for us to have a reminder that the electrons are negatively charged, symbolized or given a symbol by that one E, just to give them a negative charge. And in that respect, the protons are positively charged, and just give them a positive symbol like that. And for that case, the protons were confirmed to have a positive charge by Rutherford, this experiment. Of course, Rutherford was doing an experiment on the alpha particles, and they found out that there was a deflection, which was trying to obey the laws of attraction, which says the positive or the same charges attract, the same charges repel while the opposite charges attract. Now, the Rutherford and Chadwick discovered the nucleus, and this one, as they said, it contains a negative charge. So these particular characteristics of the subatomic particles are going to give us a clue on how organic compounds are formed in as far as bonding is concerned. So that is the reason as to why we had to look at them. And in totality, the aspect of an element, matter, an element, and an atom that we have looked into is very important, because the study of an atom gives us a basis for understanding the nature of chemical reactions, the properties of matter, and also can assist us in predicting how a reaction goes. So for that case, in organic chemistry, we're going to encounter some reactions, and we're going also to be asked to describe some of the properties of organic compounds, and also try to see some of the compounds and maybe try to see what they will result into, maybe due to, maybe when they are subjected to particular conditions. So for that case, we will round up the discussion about that particular fundamental aspect of matter, that is about elements and atoms, in so far as the history of this particular part is concerned. So for that case, in organic chemistry, we have a particular way in which we are going to represent elements, and this one does not deviate from the normal ways that we know, but of course it's good for us to remind ourselves how we are going to represent these elements in organic chemistry. So or just symbols, you can just write symbols. Of course, this is not going to deviate from the normal way that we know. For instance, the symbol for sodium will just be written as Ma. This is for sodium. The symbol for carbon will be written as C. And then the symbol for nitrogen will be written as N, capital N. I want us to understand the difference between these two in a way that when we're writing symbols of elements, the first one starts with a capital letter, while the preceding one is written in lowercase. For instance, for the sake of sodium, you can see that it's capital Na. Of course, majority of these symbols are maybe an abbreviation of their first letter of their names, or maybe the first letter of names, and some of them are derived from the Latin or the German names, or maybe some of the exceptions that we're going to encounter, but much of them just are restricted within this context. For instance, sodium, this is given a different name apart from the initial of its name. But for carbon, as you can see, it's the initial. Carbon and nitrogen is the initial there, names which are being given there. Now, this one also, apart from symbols, there's a way in which we are going to represent the atoms as we go ahead. Or these are just atoms. There's a way in which we're going to represent elements as we go ahead. And also this is very important for us to know, because at some level we'll be just required to write only symbols of elements to demonstrate for the reactions or bonding of these particular organic compounds. Now, generally we represent an element. This is a general term. Now, in this case, this is a general representation of an element. Now, this one is important because it assists the community, or maybe the scientist community, to have a general way of trying to represent information, so that that one can avoid confusion. So whenever an element can be carbon, nitrogen, sodium is represented in this particular order. This one, the X stands, this is for a symbol for element. And then Z represents the atomic number. Of course, we're going to learn about this in the atomic number and atomic weights. Atomic number, while A represents the mass number. This is just a short form of the name number. So when an element in chemistry is represented as this, X represents the symbol of an element, so we can substitute this one for carbon. And this one, A, represents the mass number, while Z represents the atomic number. Now, this kind of representation, A is a summation of Z plus N, where N represents the number of neutrons. You see, that's why it was important for us to capture the concept of an atom. Remember from the Niels Rutherford's representation of an atom, which appears like this. Maybe I can just give a rough sketch. This is a nucleus, and then this is an energy level. So we call this one Bohr-Rutherford representation of an atom. So that one is a model that was derived from Bohr and Rutherford's explanation of what an atom looks like. So for that case, the neutrons and the protons are located at the center, well, according to Niels Bohr, the electrons orbit the nucleus. So for that case, N represents the number of neutrons, while Z represents the atomic number. So for that case, A, which is a mass number, is a sum of atomic number and then the number of neutrons. So later on we shall look at what exactly refers to this particular atomic number, mass number. Now for that case, the atomic number and the mass number in summary, as we have said, the number of protons and then the number of neutrons make up the sum of the atomic number. So so finding out the number of protons, Z, and the number of neutrons, N, at the center there gives us the mass number. Remember, as Rutherford postulated that much of the weight of an atom is put at the center, because if you look at the ratio between mass of electrons, mass of a proton, and mass of the neutron, mass of electron is very small to actual to the magnitude of roughly 10 to -4, or maybe we can say, giving an estimate is to that percentage of the weight of the protons and the neutrons, which of course are almost equal to one another. So for that case, this implies that electrons have a very small amount of weight, and then the protons and the neutrons, that is what makes up much of the mass of an atom. So in that case, if we look at these two particular examples, they're going to give us a summary of what the mass number and then the number of protons and neutrons are. Look at this case of these two particular elements. That is a symbol for uranium. Uranium is a radioactive element. We're going to discuss that one under radioactivity, but we shall use it for now. So that's a symbol for uranium. As we said that up here is the mass number. So this is uranium mass number 235. And this is the atomic number, which is 92. And then this is uranium 238 with the mass number 238 and atomic number 92. So for this case, we said that this represents A, while this one represents Z, while this one represents A. This is the mass number, and this is the atomic number, or the number of protons. So in that case, if you find the difference between this one and this one, if at all our equation that we said A is equals N plus Z, these are protons, and these are neutrons. If at all our equation is true, then we will find that addition of the protons and the neutrons will give us a mass number. So the difference between the protons and the mass number gives us the number of neutrons. So in this case, for the two specific atoms that I've drawn, we'll find that the number of protons is equivalent to Z, and then the number of neutrons, which is N, equivalent to the difference between this one and this one, and this is going to be 143 newtons and 146 neutrons. So there's a specific term that we use to refer to, you see this one is the same element, uranium, but they have got different number of neutrons. So this particular kind of behavior results to what we call isotopes. So an isotope is an element with the same atomic number, Z, but different mass numbers, 235, 238. And in this sense, you'll find that these particular isotopes have the same chemical properties, but different physical properties. We're going to learn about chemical and physical properties when we shall talk about reactions, chemical and physical properties. But also in a way, when we do lab work, you find that these are some of the particular aspects that we're going to use in order to differentiate matter, maybe, or something that is the subject to study or understudy in the laboratories. We check about flammability and other aspects which are going to assist us to differentiate. So differentiating these two, you will find that this particular isotope and this one, they have the same chemical properties, but they have the same chemical properties, but different physical properties. So this one of them, or when matter displays such a kind of characteristics, or an element as two particular aspects, whereby the number Z is different, the mass number A is different, but the atomic number is the same, it gives what we call isotopes. And we have talked about their chemical and physical properties and how they behave different. So we shall look in depth about this, but I've introduced this one because in organic chemistry we are going to also find elements displaying different properties, and that one will assist us have a reminder when we come across that particular concept. So we are going to have a quick look also at the periodic table. Just have a mention of some aspects from the periodic table. We have talked about elements representation. and we have given them a symbol X and some letters like NaC for representing different aspects. Maybe or just it's symbolizing an element. So we give that one for sodium. We give that one for carbon. We can give another one maybe for potassium. And I mentioned earlier that naming of this particular element, as you can see, this one is taken from the first initial of its name. This one and this one are different. So for that case, these names are derived from different sources and they follow some specific rules. So in that case, we have what we call a periodic table. And this is a convenient way of trying to represent all the elements that are known so that they can be able to be located, or elements which display the same chemical or physical properties as we have mentioned earlier about the uranium, are grouped under the same category. So for that case, the symbols which are given here, sodium, carbon, and potassium, a symbol like sodium represents a single atom of sodium. So whenever this particular symbol appears in our writing or as we proceed with other elements, we are going to bear in mind that it represents a single atom of that one element, or the element itself. So in this case, a periodic table consists of a range of elements, of course, which we are going to look at later, but for now, elements in that sense, it's a few elements that appear naturally in that way, like the one that we said, sodium. And we're going to see that majority of the materials in nature are compounds or mixtures of compounds rather than free elements, as we are just demonstrating on the board. So in that case, an element of a compound, like let's say hydrogen. So an element, hydrogen, consists of a single proton and an electron orbiting around it. So it's a neutron, a proton, positively charged, and a single electron orbiting around it. So in that way, there's a specific representation that is used to show. Okay, let me demonstrate for a second. Element like carbon. Carbon has got the nucleus, that's a proton. Neutron, okay. That is Bohr-Rutherford model. So if this is the first electronic level, we're going to discuss about electronic levels. First electronic level, and then the second electronic level. For carbon, we are going to see that it consists of two energy levels in its configuration, whereby the first one consists of two electrons which are revolving around the nucleus, as we said about the Bohr-Rutherford model. And then the second, or the outermost shell, or just energy level, consists of 4 electrons. So in that case, there's a specific order in which each element's atom is being represented here using this particular model. So in that case, you'll find that some elements have maybe more than 4 electrons in their outermost energy level, or maybe less than that. So in that case, we have a particular order that this particular elements across the periodic table are being given, or the energy levels are filled from one element to another. And that one, of course, gives them their basic characteristics, which assist us in differentiating an element from another. So in this case, we are going to look at what we call the octet rule. And this is a rule from the word oct, or from the prefix oct. Octane, October, oct, octagonal. So this one represents 8. So in that case, the implication of the letter 8 is very important. It's going to give us a clue on what we refer to as when we say or talk about the term oct. So in this case, for an element, the number of electrons, so this one we call it, this one can be referred to an energy level, or just a shell or energy level. So this particular representation, we call it electronic configuration, or how the electrons appear in each particular shell. So this is the inner shell, it's the outer shell. So this outer shell has got a specific name that we refer to as the valence shell. So in nature, you will find that most elements, as they are arranged in the periodic table, the valence shell is either consisting of full number of electrons. Full in this sense, I'm going to use it in connection with the word octet, which means that the shell, or the outer, or the valence shell, has got complete number of electrons, which means it has been filled to an extent that it cannot take more electrons. In other cases, you'll find that the number of electrons in the outer shell are very minimal. In that sense, we are going to see how these particular aspects of maybe lacking electrons or having electrons full act in order to determine the chemical properties of an atom. So in most cases, the charge of the nucleus and the number of electrons in the valence shell determine the chemical properties of an atom. So the octet rule comes in this case in that whenever an atom of this particular nature appears, there's a filling order that we're going to learn about, whereby the first energy level will consist of a maximum of 2 electrons, and then the second energy level as well will consist of a maximum of 2 electrons, 8 electrons, and the third one. Now in this case, proceeding from here, there's going to be a variation, and this one is not applicable to all elements, as we shall learn later, because there is a range of elements in the last part of the periodic table. What's the right that we call noble elements. Like argon, xenon, and other elements in the periodic table that are of course inactive, which means they do not involve in a chemical reaction. They are inert in actual sense. So that means their outermost energy level are just filled, so they cannot, whenever an element is active or reactive, you'll find that it's either gaining or losing an electron. So that one dictates the element's chemical properties. For noble gases, the outermost shell is simply filled, so which means they cannot be able to get involved in a reaction. So this appearance of this particular number, especially the second shell and the others that are preceding, whereby they filled with electrons and they require no more, is what we call the octet rule. So for majority of the elements with energy levels that are requiring 8 electrons to be filled, Whenever that condition has been reached, then we refer to that state as a stable state for that element. Now, there's an exception whereby if an element's first energy level, or an element like hydrogen that consists only of the first energy level, like this, with a single electron, now it will only require to gain 2 electrons to make it stable and obey the octet rule. Remember, from the periodic table we have hydrogen, and helium appears in the column of noble elements which obey the octet rule. So in that case, helium is stable. So for hydrogen to attain the electronic configuration of helium, which is 2, it will have to bond with another hydrogen on an element of the same property. So which means an atom of hydrogen will bond with another atom of hydrogen to form a bond which is similar to the one that is being displayed by helium, to attain what we refer to as an octet rule. Of course, the valence shell, or the energy level of the outermost, is not filled with 8 electrons, but in that case, because of its stability, we refer to that one as attaining of the octet rule. So for that case, we have said that the outer of the shell, outer or valence shell of an atom dictates its chemical properties. Now, this bonding that I've illustrated here on the board of hydrogen and hydrogen, whereby they share the electrons, of course, the nucleus, which consists of the protons in between here, provide the attraction which enable bonding of these particular 2 atoms. Now, this one form what we call a diatomic molecule. Most gases assume this particular kind of nature naturally. So like hydrogen, oxygen, they appear in form of diatomic molecules. This kind of bonding that is appearing here is what we refer to as a covalent bond, whereby, like in this case, each contains a single electron, which come closer to achieve the same configuration as the one we have talked about. So for that case, we have what we call also ionic bonds, whereby you find that elements that form ions in nature. For instance, we have said that most elements do not exist in their stable states, so maybe they are in form of compounds, or maybe like in solutions for inorganic compounds. We are going to talk about inorganic compounds. They appear in form of ions. Let's see, for example, the sodium and chlorine. When they are in ionic form, they form what we call sodium chloride. Of course, we are going to see now the difference. Chlorine appears in the group 7 of elements, which means for it to attain an octet, it gains an electron, the gate field. That electron is given by sodium, which consists of only a single electron, its valence shell, which means it donates to chlorine to form a compound. Now, this compound in solution form is what we call an ionic compound, or generally just an ionic compound. So, for bonding of these particular compounds, they do not display the covalent bonds that we talked about, but rather they will form a configuration, or just a compound of this nature, whereby opposite charges are going to align themselves towards the respective opposite charges of the different ions. So for that case, this compound forms what we call an ionic bond. Now, apart from the covalent bonds, we have also ionic bonds. which we're going to look at so during the formation of this particular compound. So for that case, most of the organic compounds that we are talking about are linked by covalent bonds. So as we have just had a look at that particular summary of the atoms, elements, matter, the kind of bonding, the behavior from the periodic table, I hope that it's going to give us a clue on how to maneuver around those challenges in case we come across one. Now, as we said about the valence electrons or the valence shell, the outermost shell that consists of electrons is known as the valence shell, and it consists of what we call the valence electrons in this case. Now, valence electrons, as we say, are the one that dictate the chemical properties of an element. So in the case of bonding, we're going to get that the valence electrons are the ones which are going to be involved in bonding. Now we have what we call electron dot notation. So as we can see, as I've been demonstrating about the hydrogen, I've been using a dot to represent that, and when it was bonded to another hydrogen, I gave an illustration that appeared like this. So for that case, for us to show the an element that is being bonded to another one, we only show the valence electrons and ignore the ones that appear maybe in the adjacent inner energy level. For instance, if I talk about carbon as an element, we said that its configuration is 2,4, so which means the inner shell consists of 2 electrons. This is the nucleus, and the outer shell consists of 4 electrons. So in giving an electron dot notation, we'll only be required to demonstrate the 4 electrons that appear in the outermost energy level. Therefore, for carbon, it will appear